Welcome to the Drowsy Astronaut, where we explore the hidden depths of the universe. Because every detail, no matter how small, changes how we understand the whole. Tonight we're going to talk about stars, how they're born, how they live, and how they die. And we'll take our time with it, moving slowly, letting each idea settle before we move to the next. This is a long story, and we're in no rush to finish it. You may stay awake for all of it, or you might fall asleep in 10 minutes. Either way is fine, because the universe doesn't mind, and neither do I. We're just here together. If you're comfortable, take a slow breath, let your shoulders drop, and we'll begin this quiet walk through space, where time moves differently and nothing demands your attention. Before we start, I'd love to know where you're listening from tonight. Maybe drop a comment. It's always nice to know that people from so many places tune in to the same quiet corner of the internet. And if you're new here, or if you've been here before and found it helpful, you're always welcome to subscribe. Although there's no pressure, just know that we do this often, exploring topics slowly. This isn't a lecture, and there's nothing here you need to remember for later. Think of it more like sitting beside someone who's describing a long view, pointing things out as they appear, and feeling that soft heaviness that comes when your body knows it's safe to let go. What we'll do tonight is trace the life of a star, from the cold clouds where they form, to the long, steady burning, the changes with age, and the quiet or violent ways they come to an end. We'll talk about gravity, about fusion, about timescales that stretch across billions of years. And I'll keep the language simple, explaining what things mean before I name them so nothing feels like a wall. By the end, if you're still awake, you'll have a sense of how stars move through stages, and how mass decides almost everything about brightness and lifespan, and what happens when the fuel runs out. But for now, just settle in and let the words wash over you. We're going to start in the darkness between stars, where everything begins, and we'll move forward from there. Stars are not eternal, though they burn for spans so long that human history feels brief. And each one follows a path written by its starting mass, set from the very beginning. They form in clouds, burn through stages, then fade or explode, depending on how much matter they gathered. And the universe recycles what remains, over and over again. We trace that cycle from beginning to end, visiting nurseries and remnants, watching how gravity shapes everything patiently across billions of years. The story begins in darkness, in cold regions between existing stars, where hydrogen drifts in thin veils that span light years without shine, invisible and silent. These regions are called molecular clouds, vast accumulations of gas and dust, and they can stretch across dozens or hundreds of light years in every direction. Inside them, temperatures drop to just tens of degrees, above absolute zero, and densities remain low compared to air. But compared to interstellar space, they are thick. Hydrogen dominates the mixture, with helium second, and traces of heavier elements scattered throughout. And dust grains provide surfaces where molecules can form, building complexity in the cold. The clouds appear dark when seen against background stars, blocking light rather than emitting. And astronomers call these patches dark nebulae, or absorption clouds, marking where stars may be born. Gravity acts on every particle, pulling inward with patient force. But the cloud resists collapse through internal pressure and turbulent motion, holding a fragile balance. For long periods, the cloud simply drifts, neither growing nor shrinking, held in rough balance between expansion and contraction, stable for millions of years. But when something disturbs that balance, when a shockwave from a nearby supernova passes through, or when clouds collide, compression begins and the equilibrium breaks. The added pressure pushes material together, raising density in certain pockets. And once density crosses a threshold, gravity takes over and collapse becomes inevitable. A region within the cloud begins to contract, pulling surrounding gas inward. And as it shrinks, it heats slightly from compression, warming degree by degree. This forming clump is called a protostellar core, and it may span a few thousand astronomical units, growing denser and warmer as matter falls inward. The infall continues for thousands of years, and the core's center grows hotter, steadily climbing in temperature, approaching the conditions needed for fusion. At this stage, the object is not yet a star, but it glows faintly in infrared, hidden inside thick cocoons of dust that block visible light, keeping it invisible to our eyes. Rotation matters here, because the original cloud had some net spin, and as material contracts, that spin accelerates through conservation of angular momentum, spinning faster. The infalling gas can't fall straight in, so it forms a rotating disk around the growing core, and this disk feeds material gradually, steadily onto the protostar. Jets often emerge perpendicular to the disk, shooting gas outward at high speed, driven by magnetic fields that thread through the rotating matter, channeling energy into narrow beams. These jets can stretch for light years, and they carve visible cavities in the surrounding cloud, marking the presence of young stars still hidden within their dusty cradles. As the core continues to gather mass, its center grows steadily hotter, and pressure builds until the core can support itself against further collapse, reaching a temporary balance. The protostar enters a phase called the T Tauri stage, named after a variable star observed in Taurus, and it remains embedded in its disk for roughly 1 million years. During this time, the object is not yet fusing hydrogen steadily, but it shines from gravitational contraction, releasing energy as it slowly shrinks, moving toward equilibrium. Strong stellar winds begin to blow away surrounding material, and the disk gradually thins, dispersing into space, revealing the young star to outside observers. Eventually, the core temperature reaches about 10 million degrees, and hydrogen nuclei begin to fuse into helium, releasing energy through the process called nuclear fusion. This marks the birth of a true star, because fusion provides steady outward pressure, balancing gravity's inward pull in a stable equilibrium. The star settles onto the main sequence, a long stable phase, where it will spend most of its life, and its position on that sequence depends entirely on mass. A star like our Sun will remain on the main sequence for roughly 10 billion years, while more massive stars burn far faster and less massive stars far slower. Mass determines everything, from brightness to lifespan to final fate, and the range spans from less than 1/10 to over 100 solar masses. Low-mass stars, those below half a solar mass, burn hydrogen slowly through a process called the proton-proton chain, and they shine faintly in red and orange. These stars live for tens or hundreds of billions of years, far longer than the current age of the universe, so none have yet reached old age. Higher mass stars use a different fusion cycle called the CNO cycle, where carbon, nitrogen, and oxygen act as catalysts, and they burn hydrogen much faster. A star 10 times the Sun's mass might last only 20 million years, on the main sequence burning brilliantly in blue and white light, but dying young. The more massive the star, the hotter its core, and the faster it consumes its fuel, creating a steep relationship between mass and lifetime. This relationship means that the brightest stars are also the youngest, because they cannot sustain their brilliance for long spans, burning out quickly in cosmic time. When we look at a cluster of stars, we can estimate its age by noting which masses have already left the main sequence. Fusion in the core converts hydrogen into helium, and each reaction releases a tiny amount of energy, but the sheer number of reactions produces immense power. 4 hydrogen nuclei combine to form one helium nucleus, and the mass difference converts to energy through Einstein's equation, with photons carrying that energy outward. Those photons scatter millions of times as they move through dense stellar material, taking thousands of years to travel from core to surface. Once they escape the surface, they travel freely through space, and some eventually reach Earth, warming our skin and lighting our days, carrying ancient energy. During the main sequence phase, the star remains in steady balance, neither expanding nor contracting, and its luminosity and temperature stay roughly constant year after year. The core gradually fills with helium ash, because helium nuclei are too cool to fuse further at main sequence temperatures, and they simply accumulate. As hydrogen depletes in the core, fusion moves outward into a surrounding shell, and this shell burning causes the star to begin evolving, changing its structure from within. The exact path of that evolution depends on mass, and the stages that follow separate low-mass and high-mass stars, creating different endings. For stars like the Sun, the transition away from the main sequence begins when the core runs out of hydrogen and fusion ceases in the center, leaving only helium. With no outward pressure from fusion, the core contracts under gravity, and this contraction heats the core through compression, raising temperatures even without fusion happening. The rising temperature ignites hydrogen fusion in a shell around the inert helium core, and the energy from this shell burning pushes the outer layers outward. The star expands dramatically, growing hundreds of times larger, and its surface cools to red or orange hues, entering the red giant phase, swelling into space. Red giants are massive in size but relatively cool at the surface, and they shine brightly because of their enormous area, despite the lower surface temperature. The core continues to contract and heat, while the outer envelope swells and thins, creating a structure with extreme contrasts in density and temperature layered through the star. Eventually, the core reaches about 100 million degrees, and helium nuclei begin to fuse into carbon, releasing energy in a process called the triple alpha reaction. This helium burning stabilizes the core temporarily, and the star settles into a new balance, though this phase lasts far shorter than the main sequence. For the Sun, helium fusion will last only about 100 million years, a brief interval compared to its 10 billion year main sequence life, a flash in comparison. The outer layers continue to lose mass through stellar winds, shedding material into space, and this mass loss becomes significant as the star ages, blowing away its envelope. When helium runs out in the core, the pattern repeats, with helium fusion moving to a shell and the core contracting further, heating again, seeking the next stage. But for stars of solar mass, core temperatures never rise high enough to fuse carbon, and the evolution reaches a limit, a final boundary, beyond which fusion cannot continue. The core becomes a dense sphere of carbon and oxygen, no longer generating energy, and it is supported only by electron degeneracy pressure, a quantum force. This pressure arises from quantum mechanics, preventing electrons from occupying the same state, and it can hold up the core even when fusion stops. Meanwhile, the outer layers continue to expand and shed, driven by pulsations and strong winds, and eventually those layers detach completely, drifting away into space. The escaping gas forms a glowing shell around the dying star, illuminated by ultraviolet light from the exposed hot core shining through the expanding material. This shell is called a planetary nebula, though it has nothing to do with planets, and it expands outward at tens of kilometers per second. The nebula glows in reds, greens, and blues as different elements emit light at specific wavelengths, creating intricate shapes influenced by magnetic fields. The central star, now stripped to its core, is extremely hot and small, shining intensely in ultraviolet, but fading as it cools, slowly dimming over time. This remnant is called a white dwarf, a stellar ember about the size of Earth, but containing as much mass as the Sun, compressed into a tiny sphere. White dwarfs hold no active fusion, and they shine only from stored heat, glowing dimly as they radiate leftover thermal energy, fading across billions of years. The material inside is degenerate, meaning electrons are packed so tightly that quantum rules prevent further compression, and this pressure alone supports the star's weight. A teaspoon of white dwarf material would weigh several tons on Earth, because densities reach about 1 million times denser than water, crushing atoms into tight configurations. The surface temperature can start above 100,000 degrees, but with no internal fuel, the dwarf cools gradually, shifting from white to yellow, then red, and finally black. Cooling takes an extraordinarily long time, longer than the current age of the universe, so no white dwarf has yet cooled completely, and all still glow faintly, holding ancient warmth. These objects drift through space as silent remnants, no longer evolving in dramatic ways, simply radiating heat into the dark, waiting for equilibrium with the cosmic background. Some white dwarfs show pulsations, regular brightness changes, caused by internal vibrations, and astronomers study these oscillations, learning about the interior structure through stellar seismology. Others have atmospheres of pure hydrogen or pure helium, separated by gravity into layers, with the lightest element floating on top, forming a thin skin over the degenerate core. If a white dwarf has a companion star nearby, orbiting in a close binary system, material can flow from the companion onto the dwarf, accumulating on its surface in a slow stream. This transferred matter is usually hydrogen, and it piles up in a thin layer, compressing and heating under the dwarf's strong gravity, building pressure steadily. Eventually, the accumulated hydrogen reaches a critical density and temperature, and fusion ignites suddenly across the entire surface in a violent runaway reaction called a nova. The explosion blows away the accumulated layer, brightening the system by thousands of times, and the process can repeat every few decades or centuries, cycling through outbursts. Novae are not the end of the white dwarf. They simply clear the surface, and the dwarf remains intact, ready to gather more material, continuing the cycle indefinitely. But if the white dwarf gains enough mass to approach about 1.4 solar masses, it reaches a limit called the Chandrasekhar limit, and electron degeneracy pressure can no longer support the star. At that threshold, the core collapses suddenly, triggering runaway fusion of carbon and oxygen throughout the entire star, detonating in a Type Ia supernova. The entire white dwarf is destroyed in seconds, converting its mass into energy and heavy elements, and the explosion shines briefly as bright as an entire galaxy of stars. Type Ia supernovae are remarkably uniform in brightness because they always occur at nearly the same mass, and astronomers use them as standard candles, measuring distances across billions of light years. These explosions enrich the interstellar medium with iron, nickel, and other heavy elements, scattering nuclei that formed inside stars back into space, where future generations of stars will incorporate them into new systems. The uniformity of Type Ia events makes them powerful tools for mapping cosmic expansion, and observations of distant supernovae revealed that the universe's expansion is accelerating, leading to dark energy. So white dwarfs contribute both to cosmic chemistry and to our understanding of the universe's fate through their final explosive transformations. Now let's turn to more massive stars, those born with significantly more than 8 solar masses, because their lives follow a different script, burning hotter, evolving faster, and ending in violence rather than gentle fading. A massive star races through the main sequence, consuming hydrogen in just millions of years. And when the core hydrogen is exhausted, it doesn't simply stop, it continues fusing heavier elements. After hydrogen runs out, the core contracts and heats to higher temperatures, until helium fusion begins, forming carbon and oxygen just as in lower mass stars, but the process doesn't end there. When helium depletes, the core contracts again, and temperatures rise high enough to fuse carbon into neon and magnesium, then neon into oxygen, then oxygen into silicon. Each fusion stage produces heavier elements, and each stage lasts a shorter time because heavier nuclei yield less energy per reaction, requiring faster burning to support the star. Carbon fusion might last a few thousand years, neon fusion a few years, oxygen fusion months, and silicon fusion just days, accelerating toward an inevitable conclusion. The star develops a layered structure like an onion, with shells of different elements burning at different depths, each supported by the heat from fusion below. At the center lies an iron core, growing steadily as silicon fuses, and iron nuclei are the most tightly bound, meaning fusion of iron consumes energy rather than releasing it. Once the core is mostly iron, fusion stops abruptly, because no further energy can be gained, and the core suddenly loses its outward pressure, collapsing under its own immense weight. The collapse happens in less than a second, with the core shrinking from thousands of kilometers to about 20, and the implosion releases a staggering amount of gravitational energy. Electrons are crushed into protons, forming neutrons and releasing neutrinos, and the core becomes incredibly dense, approaching the density of an atomic nucleus, packed beyond imagination. The collapsing material hits this dense core and rebounds, sending a shockwave outward through the star, and this shockwave tears the star apart in a core collapse supernova explosion. The explosion is extraordinarily bright, radiating more energy in a few weeks than the Sun will emit in its entire 10 billion year lifetime, outshining billions of stars. The outer layers of the star are blown into space at speeds exceeding 10,000 kilometers per second, and the blast wave sweeps up surrounding gas, creating an expanding shell of glowing debris. This debris contains all the elements formed during the star's life, including carbon, oxygen, silicon, iron, and heavier elements synthesized in the explosion itself through rapid neutron capture. Elements heavier than iron, like gold, platinum, and uranium, form only in these extreme conditions when neutrons flood the environment, building massive nuclei in seconds. The material spreads outward, mixing with the interstellar medium, and it will eventually join molecular clouds, where future stars and planets and possibly life will form from the enriched gas. Every atom of carbon in your body, every breath of oxygen, was forged inside a star and scattered by a supernova billions of years ago. We are made of stellar remnants, literally composed of material that cycled through ancient stars, died in explosions, and drifted through space until gravity gathered it again. This connection is not poetic metaphor. It is direct, physical ancestry, linking human existence to the life cycles of stars through the atoms we carry. At the center of the supernova, the collapsed core remains, and depending on its mass, it becomes either a neutron star or a black hole, both extreme endpoints. Neutron stars are incredibly small, only about 20 kilometers across, yet they contain more mass than the Sun, making them the densest objects aside from black holes. A sugar cube of neutron star material would weigh about 1 billion tons, and the gravity at the surface is so strong that escape velocity approaches half the speed of light. These objects spin rapidly because as the core collapsed, conservation of angular momentum accelerated rotation, and some neutron stars spin hundreds of times per second. Many neutron stars have intense magnetic fields, trillions of times stronger than Earth's, and these fields channel radiation into beams emerging from the magnetic poles. As the star rotates, the beams sweep across space like lighthouse beams, and if Earth lies in the path, we detect regular pulses, calling the object a pulsar, ticking with clockwork precision. Pulsars were first discovered in 1967 by Jocelyn Bell Burnell, and their regularity was so precise that early speculation wondered if they might be artificial signals. The pulses arrive with incredible consistency, some varying by less than a microsecond over years, making pulsars among the most accurate clocks in the universe. Timing these pulses reveals details about the neutron star, including its spin rate, magnetic field strength, and whether it orbits a companion through Doppler shifts in the pulse timing. Binary pulsars, systems where two neutron stars orbit each other, lose energy by emitting gravitational waves, and observations of their orbital decay provided the first indirect evidence for gravitational radiation. The detection of gravitational waves directly in 2015 came from merging black holes, but neutron star mergers were detected soon after, confirming predictions and opening new observational windows. When two neutron stars spiral together and merge, the collision produces a brief burst of gamma rays, gravitational waves, and a kilonova, a unique explosive event rich in heavy elements. The merger creates conditions even more extreme than a supernova, flooding space with neutrons and synthesizing huge quantities of gold, platinum, and other heavy elements in rapid nucleosynthesis. Observations in 2017 detected both gravitational waves and light from such a merger, allowing astronomers to confirm that neutron star collisions are major sources of the heaviest elements in the universe, so gold in jewelry and platinum in electronics likely formed in these violent cosmic collisions billions of years ago, forged in the chaos of merging stellar remnants. If the core left behind by a supernova exceeds about 3 solar masses, not even neutron degeneracy pressure can support it, and the collapse continues without limit, forming a black hole. A black hole is a region where gravity is so strong that nothing, not even light, can escape once it crosses the event horizon, the boundary of no return. The event horizon is not a physical surface, but a mathematical boundary, marking the point where escape velocity equals the speed of light, sealing the interior from outside view. Anything that crosses the horizon is lost to the outside universe, falling inward toward a singularity, a point of infinite density, where known physics breaks down completely. Black holes don't pull harder than other objects of the same mass. They simply compress that mass into a space so small that extreme gravity dominates close to the center, warping space-time dramatically. If the Sun became a black hole, Earth's orbit would remain unchanged because the Sun's mass would still be the same, only concentrated into a 3-kilometer sphere. Of course, the Sun will never become a black hole because it lacks the mass, but the thought experiment shows that black holes are not cosmic vacuum cleaners. They obey the same gravity laws. What makes them unique is the event horizon, the point beyond which information cannot escape, creating a one-way membrane, separating the interior from the rest of the universe. Detecting black holes is challenging because they emit no light, but astronomers find them through their effects on nearby matter, watching how surrounding material behaves in extreme gravity. When a black hole has a companion star in a binary system, it can pull gas from that star, and the infalling material forms an accretion disk spiraling inward toward the event horizon. Friction in the disk heats the gas to millions of degrees, and it radiates intensely in X-rays before disappearing across the horizon, making the black hole visible through its feeding process. Some black holes launch powerful jets perpendicular to the disk, shooting material outward at nearly the speed of light, channeling energy into narrow beams that stretch across light years. Stellar mass black holes, those formed from collapsing stars, range from about 3 to dozens of solar masses, and they're scattered throughout galaxies, hidden unless they interact with visible matter. Supermassive black holes sit at the centers of most galaxies, including our own Milky Way, and they contain millions or billions of solar masses, far beyond what stellar collapse alone could produce. How supermassive black holes formed remains an open question, with theories ranging from direct collapse of massive gas clouds to gradual growth through mergers to seeds left from the very early universe. The black hole at the Milky Way's center, called Sagittarius A star, has about 4 million solar masses, and astronomers have tracked stars orbiting it, mapping their paths with extraordinary precision over decades. These orbits confirm the black hole's mass and location, because the stars move at thousands of kilometers per second, whipping around an invisible gravitational anchor, following ellipses that match predictions perfectly. In 2019, the Event Horizon Telescope collaboration released the first image of a black hole's shadow, showing the dark silhouette against glowing gas in the galaxy Messier 87, 55 million light-years away. The image matched theoretical predictions, with a dark central region surrounded by a bright ring, and the achievement required coordinating radio telescopes across the entire planet, creating an Earth-sized virtual dish. A similar image of Sagittarius A star followed in 2022, confirming that our galaxy's central black hole also fits general relativity's predictions, validating Einstein's century-old framework in the strongest gravity we can observe. Black holes evaporate extremely slowly through Hawking radiation, a quantum effect where particle pairs form near the horizon and one escapes while the other falls in, causing the black hole to lose mass. For stellar mass black holes, this evaporation takes far longer than the current age of the universe, so effectively they persist indefinitely, but in the distant future, trillions of years hence, even black holes will fade. This process means black holes are not truly eternal, though their lifetimes stretch beyond imagination, and the final stages of evaporation would release energy in a burst as the last mass disappears. The universe's ultimate fate may be a cold, dark expanse, filled only with evaporating black holes, decaying particles, and ever-expanding space in a state called heat death, where entropy reaches maximum. But that's far in the future, trillions upon trillions of years away. And for now, stars continue forming, living and dying, cycling matter through generations, enriching the cosmos with each iteration. Each generation of stars inherits material from previous generations, so the universe's chemical complexity grows over time, building heavier elements with every stellar death, gradually changing the makeup of galaxies. The very first stars, born a few 100 million years after the Big Bang, contained only hydrogen, helium, and traces of lithium, the primordial elements forged in the universe's first minutes. These stars are called population 3 stars, and none have been directly observed because they formed so long ago, but their existence is inferred from theory and from the chemistry of later stars. Population 3 stars were likely very massive, perhaps hundreds of solar masses, because the absence of heavier elements made it harder for gas clouds to cool and fragment, favoring larger collapses. They burned incredibly hot and bright, living only a few million years before exploding as supernovae, seeding space with the first carbon, oxygen, and iron, initiating cosmic chemical evolution. Their remnants mixed into the interstellar medium, and the next generation of stars, called population 2, formed from slightly enriched gas containing trace metals, enough to alter their formation and evolution. Our Sun belongs to population 1, the most recent generation, forming from gas already enriched by billions of years of stellar recycling containing about 2% heavy elements by mass. This enrichment made rocky planets possible because planets like Earth require silicon, iron, oxygen, and other heavy elements which didn't exist in the early universe. only appearing after many stellar generations. So life depends on stellar death. Quite literally, because without supernovae scattering heavy elements, there would be no rocks, no water, no complex chemistry, no biology anywhere. The atoms in your bones, the iron in your blood, the oxygen you breathe, all formed in stars, forged through fusion and explosion, then gathered by gravity into new systems, eventually becoming you. This deep connection ties human existence to the cosmos, making us not separate observers, but participants in a vast cycle built from stardust, shaped by time, products of the universe contemplating itself. Stellar nurseries continue forming stars today, in regions like the Orion Nebula, the Eagle Nebula, and the Carina Nebula, vast clouds where thousands of stars are being born right now. Telescopes like Hubble and James Webb have captured detailed images of these regions, revealing pillars of gas, glowing shells, and infant stars still wrapped in their birth cocoons, showing the process in action. The pillars of creation in the Eagle Nebula are towering columns of gas and dust, several light-years tall, sculpted by intense radiation from nearby young stars, eroding slowly but creating beautiful structures. Inside those pillars, dense pockets of gas are collapsing, forming new protostars, even as the surrounding material is blown away, demonstrating the ongoing cycle of destruction and creation. Young stars often form in clusters because molecular clouds fragment into many pieces, and dozens or hundreds of stars can emerge from a single cloud within a few million years. These clusters gradually disperse as stars drift apart, influenced by gravitational interactions and the galaxy's overall rotation, scattering young stars across wider regions over time. Our Sun likely formed in such a cluster, along with thousands of siblings, but over 4.6 billion years, those sibling stars have drifted apart, now scattered throughout the Milky Way. Some may still exist, with similar ages and compositions, and astronomers search for solar siblings, analyzing stellar chemistry, trying to identify stars that share the Sun's birth cloud. Star formation rates vary across galaxies, with some galaxies producing hundreds of solar masses of new stars per year, while others, like the Milky Way, form only a few solar masses annually. Starburst galaxies undergo intense episodes of star formation, often triggered by galaxy collisions, where merging gas clouds compress and collapse, igniting massive bursts of stellar birth across short timescales. These bursts produce brilliant ultraviolet light, and the resulting supernovae inject energy into the gas, sometimes halting further star formation in a self-regulating feedback loop that shapes galaxy evolution. Over cosmic time, star formation rates have declined as galaxies consumed their gas reserves and as the universe's expansion spread matter more thinly, making future star formation less frequent. Eventually, the universe will form its last star, perhaps trillions of years from now, when the remaining gas is exhausted and no new clouds gather to collapse, ending an era that began with the first light. After that, existing stars will simply age and die, one by one, until the universe contains only remnants, white dwarfs cooling, neutron stars spinning, black holes waiting in an ever-darkening cosmos. This distant future seems bleak, but it also reflects the preciousness of the current era, when stars still shine, planets still orbit, and complexity still flourishes in a universe rich with energy. We exist in a golden age of stars, surrounded by light, warmth, and the potential for life, a temporary window in the universe's vast timeline before darkness becomes permanent. For now, we return to the present, to the stars that fill our night sky, and to the details of their final stages, tracing the paths not yet fully covered, moving carefully through each transformation. Remember that mass is the defining factor, determining whether a star ends as a white dwarf, a neutron star, or a black hole, and the boundary between these fates lies around 8 to 10 solar masses. Stars below that threshold lose their outer layers gradually, through stellar winds and planetary nebulae, leaving behind white dwarfs, while more massive stars explode violently, scattering their remains across space. But there are subtleties within these categories, including stars that undergo partial explosions or that lose mass in unusual ways, creating outcomes that fall between the standard endpoints. Some massive stars lose enormous amounts of mass through winds, especially during late evolutionary stages, and if they shed enough material, they may avoid supernova explosions, dying more quietly than expected. Wolf-Rayet stars are examples of this. Massive stars that have lost their hydrogen envelopes entirely, exposing helium and carbon layers and blowing powerful winds that carry away several Earth masses per year. These winds are driven by intense radiation pressure, where photons from the hot core push outward on ions, accelerating gas to thousands of kilometers per second, stripping the star layer by layer. By the time a Wolf-Rayet star reaches the end of its life, it may have shed so much mass that the remnant core falls below the threshold for black hole formation, collapsing instead into a neutron star. The boundary between neutron stars and black holes is not perfectly sharp, because the exact transition mass depends on the core's composition, rotation, and magnetic fields, all influencing the final structure. Some supernovae leave behind neutron stars that later collapse into black holes, if they accrete additional matter, or if their internal pressure weakens, demonstrating that remnant types can change over time. Conversely, some massive stars may collapse directly into black holes, without producing a visible supernova, because the implosion doesn't generate a strong enough shockwave, and the material simply falls inward silently. These events are called failed supernovae, and they would appear as stars that suddenly vanish, disappearing without explosion, leaving behind only a black hole, hidden from direct detection. Observations have tentatively identified a few candidate failed supernovae, where massive stars disappeared from view without brightening. But confirming these events requires careful analysis, ruling out other explanations like dust obscuration or variability. The variety of stellar endpoints shows that nature is more complex than simple categories suggest, and each star's death is shaped by its unique history from formation through all evolutionary stages. Binary systems add another layer of complexity, because two stars orbiting closely can interact, exchanging mass, altering each other's evolution, and sometimes merging, creating outcomes impossible for isolated stars. When a massive star in a binary loses its envelope to a companion, the exposed core evolves differently than it would alone, and the eventual explosion or collapse depends on how much mass transferred and when. Some binaries contain two massive stars, and both may explode as supernovae, leaving behind two neutron stars or black holes, which then orbit each other, slowly spiraling inward over millions of years. These compact binaries lose energy through gravitational wave emission, and they eventually merge in violent collisions detected by observatories like LIGO and Virgo, revealing events that release tremendous energy in seconds. The first gravitational wave detection in 2015 came from two merging black holes, each about 30 solar masses, and the signal matched predictions from general relativity with extraordinary precision. Subsequent detections have revealed dozens of such mergers, showing that black hole and neutron star collisions occur regularly throughout the universe, contributing to cosmic evolution in measurable ways. Neutron star mergers produce not only gravitational waves, but also light across the spectrum, from gamma rays to radio waves, and this multi-messenger astronomy provides rich information about extreme physics. The 2017 detection of colliding neutron stars allowed astronomers to observe the event electromagnetically as well, confirming that these mergers forge heavy elements through rapid neutron capture, enriching galaxies with gold and platinum. This observation resolved a long-standing mystery about where the universe's heaviest elements originate, demonstrating that neutron star collisions contribute significantly alongside supernovae to cosmic chemical diversity. The light from that merger also allowed scientists to measure the universe's expansion rate using the distance derived from gravitational waves and the redshift from light, providing an independent check on cosmological models. Gravitational waves themselves are ripples in space-time, caused by accelerating masses, and they travel at the speed of light, carrying information about events that produce them encoded in the wave's frequency and amplitude. Detecting these waves requires extraordinarily sensitive instruments because even from violent cosmic events, the ripples stretch and squeeze space by less than 1 part in 10 to the 21st, a distance smaller than an atomic nucleus. LIGO's detectors use laser interferometry, bouncing light between mirrors separated by kilometers, and measuring tiny changes in the light's travel time as gravitational waves pass through, distorting space-time itself. The success of gravitational wave astronomy has opened a new window into the universe, revealing events invisible to telescopes and allowing us to study the universe's most extreme phenomena in unprecedented ways. Returning to individual stellar deaths, we can consider how astronomers study these processes, observing supernovae, tracking light curves, and analyzing spectra to understand what happens when massive stars explode. Supernovae are classified by their spectra and light curves into types based on which elements appear and how brightness changes over time, with type Ia involving white dwarfs and core collapse events split into types 2, Ib, and Ik. Type 2 supernovae show hydrogen lines in their spectra because the exploding star retained its hydrogen envelope, while type Ib lacks hydrogen but shows helium, and type Ich lacks both, having shed outer layers before exploding. These classifications help astronomers understand the progenitor stars and the physical processes at work, linking observations to theoretical models of stellar evolution and explosion mechanisms. Light curves provide additional information because the brightness over time reflects how energy escapes and what powers the glow, whether radioactive decay of nickel-56, shock heating, or interaction with surrounding material. Some supernovae show plateaus in their light curves, where brightness stays roughly constant for weeks, indicating that the explosion is interacting with a dense shell of material ejected earlier by the progenitor star. Others decline rapidly, fading within days, suggesting less massive ejecta or different energy sources, and careful study of these patterns reveals the diversity of stellar explosions and their underlying physics. Supernova remnants persist long after the initial explosion, as expanding shells of gas that glow for thousands of years, heated by shocks and interactions with the interstellar medium, creating beautiful structures visible across the electromagnetic spectrum. The Crab Nebula is a famous supernova remnant, observed exploding in 1054 by Chinese and Arab astronomers, and today it remains a bright expanding cloud powered by a spinning neutron star at its center. That central pulsar spins 30 times per second, injecting energy into the surrounding nebula through powerful winds, and the nebula glows across the spectrum, from radio waves to gamma rays, fed by the pulsar's relentless rotation. Cassiopeia A is another well-studied remnant, from a supernova that occurred about 350 years ago, though no historical records confirm the sighting, suggesting it may have been obscured by dust. The remnant shows intricate filaments and knots of gas, moving outward at thousands of kilometers per second, and observations reveal where different elements concentrate, mapping the explosion's internal structure through the debris pattern. Supernova remnants eventually fade and disperse, after tens of thousands of years, blending into the interstellar medium, contributing their enriched material to future generations of stars, completing the cycle of stellar life and death. Some remnants trigger new star formation because their expanding shockwaves compress nearby gas clouds, initiating collapse and creating the next generation of stars from the ashes of the old, a poetic but accurate description. This feedback loop connects stellar generations, ensuring that death leads to birth and that the galaxy continually renews itself, with new stars forming from the remnants of old ones, maintaining a dynamic, evolving ecosystem. Our solar system formed from such enriched material, gathering elements scattered by ancient supernovae, and without those prior generations, the sun and planets could not exist, making our origins deeply tied to stellar death. Within our solar system, we find traces of those ancient stars, embedded in meteorites that fall to Earth, carrying grains of dust that predate the sun, preserving microscopic samples from earlier stellar generations. These pre-solar grains have isotopic ratios, different from solar system material, marking them as outsiders formed in other stars and carried into the collapsing cloud that became our sun and planets. Studying these grains gives direct information about the stars that made them, revealing temperatures, pressures, and nucleosynthesis processes from billions of years ago, frozen in tiny fragments no larger than bacteria. It's remarkable that we can hold pieces of other stars, touch material forged in alien cores, and analyze their chemistry, connecting us physically and historically to the broader stellar population of our galaxy. The Milky Way contains hundreds of billions of stars, at various stages of evolution, and at any moment, several stars are exploding somewhere in the galaxy, though most are too distant or obscured to see from Earth. On average, a supernova occurs in the Milky Way about once every 50 years, but dust blocks our view of much of the galaxy, so only a handful have been visible to the naked eye throughout recorded history. The most recent naked eye supernova was in 1604, observed by Johannes Kepler, and before that Tycho Brahe saw one in 1572, both carefully documenting the events and helping to overturn old ideas about celestial permanence. No supernova has appeared in our galaxy since, at least none visible from Earth, though modern telescopes detect them routinely in other galaxies, finding dozens or hundreds every year across billions of light years. When a nearby supernova does occur, within a few thousand light years, it will be spectacular, potentially visible in daylight, casting shadows at night, and offering an unprecedented opportunity for detailed study with modern instruments. The supernova would pose no danger to Earth at those distances, because harmful radiation dissipates over space, but it would be bright enough to rival the Moon, depending on the star's distance and the explosion's energy. Betelgeuse is one candidate for a future supernova, a red supergiant in Orion, about 550 light-years away, nearing the end of its life, though exactly when it will explode remains uncertain. It could happen tomorrow or in 100,000 years, because the final stages of massive star evolution are unpredictable, and astronomers watch it closely, noting changes in brightness and surface activity, searching for signs of imminent collapse. If Betelgeuse explodes, it will outshine every star in the night sky, becoming a brilliant point of light, visible even in cities, and its study would advance our understanding of supernovae enormously, given the proximity and modern observational tools. The explosion would have happened centuries ago in real time, because light takes 550 years to reach us, but we would see it unfold over weeks and months, watching the light curve rise and fall in real time from our perspective. Other nearby candidates include Eta Carinae, a massive, unstable star about 7,500 light-years away, that underwent a giant eruption in the 1840s, briefly becoming one of the brightest stars before fading again. Eta Carinae may explode as a supernova soon on astronomical timescales, or it may continue erupting periodically, shedding mass in outbursts, possibly avoiding a full supernova by losing enough material beforehand to change its fate. Stellar evolution is not entirely deterministic, because small differences in mass, rotation, magnetic fields, or companion stars can lead to significantly different outcomes, making each star's life a unique path rather than a rigid script. This unpredictability makes astronomy both challenging and fascinating, because even with strong theoretical frameworks, nature surprises us, and observations continue revealing unexpected phenomena, forcing refinements and new ideas. The discovery of gamma-ray bursts in the 1960s initially remained mysterious for decades until astronomers realized they were connected to the collapse of massive stars in distant galaxies, some of the universe's most energetic explosions. Gamma-ray bursts release as much energy in seconds as the sun will emit over its entire lifetime, focused into narrow jets. And when those jets point toward Earth, we detect intense flashes across billions of light years. These bursts are associated with hypernovae, extremely energetic supernova, where the collapsing core forms a black hole and jets punch through the star, creating beamed radiation that outshines the entire host galaxy briefly. If a gamma-ray burst occurred within our galaxy and pointed at Earth, from a few thousand light-years, it could damage the ozone layer, exposing the surface to harmful radiation, though the probability is extremely low and such events are rare. Fortunately, most massive stars are not oriented to aim jets at us, and gamma-ray bursts require specific conditions, so the risk is negligible, but the scenario illustrates the power of stellar death and its potential consequences. The universe is full of energetic processes, from stellar explosions to black hole jets to galaxy collisions, and while space is vast and mostly empty, it is also dynamic, violent, and constantly reshaping itself through gravity and energy. Despite this violence, stellar death is also creative, because it distributes heavy elements, triggers new star formation, and enriches the cosmos with the building blocks of complexity, making planets, life, and consciousness possible. Every complex molecule on Earth contains carbon, nitrogen, oxygen, phosphorus, elements forged in stars and scattered by supernovae, and without that cosmic recycling, chemistry would be limited to hydrogen and helium, far too simple for life. The entire biosphere depends on stellar nucleosynthesis, from photosynthesis that uses carbon and oxygen to DNA that requires phosphorus and nitrogen to bones and shells that incorporate calcium, all gifts from exploded stars, billions of years gone. We live on a planet made of stardust, breathing air enriched by ancient explosions, and this realization connects human existence to the deepest processes in nature, bridging the microscopic and the cosmic, the living and the inanimate. Looking outward from Earth, we see the results of stellar evolution, written across the sky in constellations, nebulae, and clusters, each telling part of the story of how stars live and die and how matter cycles through generations. The constellation Orion contains stars at many different life stages, from young, hot stars like Rigel to the aging red supergiant Betelgeuse to the Orion Nebula, a stellar nursery where stars are forming right now, a compressed cosmic timeline. Rigel is a blue supergiant, burning fiercely and destined to explode as a supernova within a few million years, though from our perspective it appears stable and eternal, shining steadily night after night. Betelgeuse, as mentioned earlier, is in its final stages, having already exhausted hydrogen and helium in its core, now burning heavier elements and approaching the end when its core will collapse and the star will detonate. The Orion Nebula, visible to the naked eye, as a fuzzy patch in Orion's sword, is a glowing cloud of gas and dust, illuminated by young massive stars that have recently ignited fusion, blasting the surrounding material with intense ultraviolet light. Inside that nebula, protostars are still forming, hidden within dense knots of dust, and infrared telescopes can peer through the obscuration, revealing hundreds of young stellar objects in various stages of birth. The trapezium cluster at the nebula's center contains 4 bright stars visible in small telescopes, but actually includes many more stars, packed densely together, all formed from the same molecular cloud within the past few million years. These stars will eventually disperse as the nebula dissipates, and gravitational interactions scatter them across the galaxy, but for now they remain clustered, bound loosely by their shared origin, drifting together through space. Star clusters come in 2 main types: open clusters like the Pleiades, containing hundreds of young stars loosely bound, and globular clusters, containing hundreds of thousands of old stars, tightly packed into spherical shapes. Open clusters are found in the galactic disk, among active star-forming regions, and they gradually dissolve over hundreds of millions of years as stars drift apart, influenced by the galaxy's gravitational field and by encounters with other objects. Globular clusters orbit in the galactic halo, far above and below the disk, and they contain some of the oldest stars in the universe, formed over 12 billion years ago, shortly after the Big Bang, preserving ancient stellar populations. The stars in globular clusters have very low metal content because they formed before many generations of supernovae had enriched the interstellar medium, and studying their chemistry reveals conditions in the early universe frozen in ancient light. These clusters help astronomers measure cosmic distances because their stars follow predictable patterns on the Hertzsprung Russell diagram, and by comparing observed brightness to intrinsic luminosity, we can calculate how far away the cluster lies, using parallax and standard candles. The Hertzsprung Russell diagram plots stellar temperature against luminosity, and most stars fall along the main sequence, a diagonal band where hydrogen-burning stars reside, with giants and supergiants above and white dwarfs below. A cluster's age can be estimated by noting where its main sequence turns off, because more massive stars evolve faster, and the most massive stars still on the main sequence indicate when the cluster formed. This method provides ages for globular clusters, confirming they're ancient, and for open clusters, showing they're young, typically only millions to a few billion years old, representing different stellar generations. Our Sun is middle-aged, about 4.6 billion years old, halfway through its main sequence lifetime, and it has another 5 billion years before hydrogen depletion forces it off the main sequence into the red giant phase. When that happens, the Sun will expand beyond Earth's orbit, engulfing Mercury and Venus, possibly Earth as well, though mass loss may push Earth outward slightly, sparing it from complete destruction, but not from sterilization. The Earth will become uninhabitable long before then, because the Sun's luminosity gradually increases with age, and within about 1 billion years the oceans will evaporate and the surface will resemble Venus, hot and lifeless, ending biology here. Life on Earth has existed for over 3 billion years, but it has less than 1 billion remaining unless technology allows migration elsewhere, making the Sun's evolution not just an abstract cosmic process, but a direct threat to our distant descendants. After the Sun becomes a red giant, it will fuse helium in its core, stabilizing briefly, but eventually that fuel will run out too, and the outer layers will drift away, forming a planetary nebula, leaving behind a white dwarf remnant, slowly cooling through the eons. That white dwarf will contain most of the Sun's mass, compressed into an Earth-sized sphere, glowing faintly from residual heat, gradually fading over billions of years, becoming a cold, dark cinder, invisible against the black of space. The planets may survive as dead worlds, orbiting the white dwarf in silence, or they may be disrupted during the red giant phase, torn apart by tidal forces, or ejected by interactions, scattering into interstellar space as rogue bodies. Either way, the solar system's story will end quietly, without violence, mirroring the Sun's modest mass and its gentle death, contrasting sharply with the explosive ends of more massive stars scattered throughout the galaxy. Thinking about the Sun's eventual fate can feel unsettling, but it also provides perspective, reminding us that everything changes, including stars, planets, and life, and that the universe operates on scales far beyond human experience. Yet within that vast scale, we exist. Conscious beings made of stellar material, capable of understanding where we came from, how stars work, and what the future holds. A remarkable achievement of matter organizing itself into thought. The fact that we can trace our origins back through stellar generations and forward to the Sun's demise demonstrates the power of scientific inquiry and the beauty of a universe that can be understood even as it dwarfs us in time and space. This understanding doesn't diminish meaning, it deepens it, connecting individual existence to the grandest processes in nature, making us participants in cosmic evolution, witnesses to the universe's unfolding story written in light and gravity. Beyond our solar system, billions of other stars follow similar or different paths, and recent decades have revealed that most stars host planets, expanding the cosmic inventory of worlds and raising questions about how common life might be. Exoplanet discoveries began in the 1990s, and today we know of thousands of confirmed planets orbiting other stars, with sizes ranging from smaller than Earth to larger than Jupiter, in orbits close and distant around stars of many types. These planets formed from the same disks that fed their parent stars, and their compositions reflect where they formed in the disk, with rocky planets near the star, where temperatures were high, and gas giants farther out, where ices and gases could accumulate. The diversity of exoplanets surprises astronomers, because many systems differ dramatically from ours, with hot Jupiters orbiting close to their stars, super-Earths larger than our planet, and systems with multiple planets in tightly packed orbits. Understanding how these systems formed requires studying planet migration, disk dynamics, and gravitational interactions, and each discovery refines models of planetary formation, revealing that our solar system is one of many possible configurations, not a universal template. Some exoplanets orbit in the habitable zone, the region where liquid water could exist on the surface, and these worlds are prime candidates for searching for life, though distance makes direct study extremely challenging with current technology. Detecting biosignatures in exoplanet atmospheres, like oxygen combined with methane, could indicate life, and upcoming telescopes like the James Webb Space Telescope are beginning to analyze atmospheres, searching for chemical imbalances that might signal biological activity. Whether life exists elsewhere remains unknown, but given the vast number of planets, the chemical building blocks widely available, and the resilience of life on Earth, many scientists consider it likely that life has emerged elsewhere, perhaps many times, throughout the galaxy. If life is common, intelligent life may be rare, because intelligence requires not only life, but also stable conditions, evolutionary pressures toward complexity and time, and many factors could prevent simple life from evolving into technological civilizations. The Fermi paradox asks why we haven't detected alien civilizations, given the galaxy's age and size, and possible answers range from life being rare to civilizations being short-lived, to communication being difficult across interstellar distances. Perhaps intelligent life tends to destroy itself through war, environmental collapse, or other catastrophes before achieving interstellar communication, a sobering thought that underscores the importance of our own civilization's survival and wisdom. Or perhaps civilizations are common but quiet, using communication methods we haven't discovered, or deliberately avoiding contact or existing at different times, so that galactic civilizations rarely overlap, isolated by vast gulfs of space and time. These questions connect to stellar evolution, because stars provide the energy and elements that life requires, and the longevity of a star determines how long life has to develop, making stellar lifetimes directly relevant to biology. Red dwarf stars, the smallest and most common, burn hydrogen so slowly that they live for trillions of years, far longer than the universe's current age, providing potentially stable environments for life to evolve over immense timescales. However, red dwarfs are also prone to flares. violent eruptions that could strip planetary atmospheres, and their habitable zones lie close to the star, where tidal forces might lock planets, creating permanent day and night sides, complicating habitability. Sun-like stars offer a middle ground, with lifetimes of billions of years, enough time for complex life to develop, and stable output that doesn't threaten planetary atmospheres, making them perhaps the best candidates for hosting life as we know it. Massive stars live too briefly, burning out in millions of years, insufficient time for life to emerge and evolve, and their violent ends would sterilize surrounding systems, making them unlikely hosts for biological complexity, despite their brilliance and abundance of heavy elements. So the type of star matters, influencing whether life can begin, survive, and thrive. And this realization narrows the search for habitable worlds, focusing attention on certain stellar types and specific orbital configurations that favor stability. The search for extraterrestrial life is intertwined with understanding stellar evolution, because we need to know which stars live long enough, which produce the right elements, and which provide stable environments to guide where we look among billions of possibilities. Even if we never find life elsewhere, the search itself deepens our understanding of stars, planets, chemistry, and biology. And it forces us to consider what makes Earth special or typical in the context of the wider universe. Returning to the mechanics of stellar death, we can explore more exotic outcomes, including events where stars don't follow the usual paths, producing rare but fascinating phenomena that challenge theoretical models and expand our understanding. Some stars undergo repeated outbursts before dying, pulsing irregularly, ejecting shells of material in waves, creating layered nebulae that reflect multiple episodes of mass loss, painting complex structures across space over thousands of years. Luminous blue variables are one such class, massive, unstable stars that vary unpredictably in brightness, sometimes dimming by several magnitudes and losing enormous amounts of mass in giant eruptions without fully exploding as supernova. Eta Carinae, mentioned earlier, is a luminous blue variable, and its 1840 eruption ejected several solar masses, creating the Homunculus Nebula, a bipolar structure that surrounds the star, still expanding outward, visible in stunning detail through modern telescopes. These eruptions may be driven by internal instabilities, where radiation pressure overwhelms gravity temporarily, or by interactions in binary systems where one star transfers mass violently, triggering outbursts, though the exact mechanisms remain debated among astronomers. Luminous blue variables eventually explode as supernovae, or collapse directly into black holes, but their pre-supernova behavior complicates predictions, and their mass loss alters the final explosion, changing how much energy releases and what remnants form afterward. Another unusual phenomenon is the pair instability supernova, which occurs in extremely massive stars above about 130 solar masses, where conditions in the core create electron-positron pairs, destabilizing the star catastrophically. In these stars, the core temperature rises so high that photons spontaneously create particle-antiparticle pairs, and these pairs don't provide the same pressure support as photons, causing the core to collapse suddenly, igniting explosive oxygen burning throughout the entire star. The explosion is so powerful that it completely destroys the star, leaving no remnant behind. and the energy release exceeds typical supernovae, shining brilliantly as the entire stellar mass converts into energy and ejected material, scattering across space with no black hole or neutron star remaining. Pair instability supernovae are thought to be rare because stars above 130 solar masses are uncommon, and they may have been more frequent in the early universe when population 3 stars formed with higher masses than stars today. Detecting these events in distant galaxies helps astronomers test models of early stellar evolution and understand how the first stars died, enriching the universe with heavy elements and shaping the chemical evolution that followed over billions of years. Some superluminous supernovae shine hundreds of times brighter than typical core collapse events, and while some may be pair instability explosions, others likely involve different mechanisms such as interaction with dense circumstellar material or magnetar formation, where intense magnetic fields power prolonged emission. Magnetars are neutron stars with extraordinarily strong magnetic fields, trillions of times stronger than typical neutron stars, and these fields can power bursts of X-rays and gamma rays, releasing enormous energy in brief flashes, making magnetars some of the most energetic objects per unit mass. The magnetic fields may form during the core collapse, if the collapsing core spins rapidly, amplifying fields through dynamo processes, though the exact origin remains uncertain, and magnetars represent an extreme subset of neutron stars with unique observational signatures. Magnetar flares can be detected across the galaxy, briefly outshining all other X-ray sources, and one famous flare in 2004 from SGR 180620 released more energy in 1/10 of a second than the Sun emits in 100,000 years, demonstrating the scale of magnetic energy stored in these compact objects. If a magnetar formed close to Earth, within a few dozen light years, its flare could damage satellites, disrupt communications, and potentially affect the atmosphere. Though such events are extremely rare, and no magnetars currently exist close enough to pose a threat. The diversity of neutron star types, including pulsars, magnetars, and quieter isolated neutron stars, shows that even within a single remnant category, conditions vary widely, depending on mass, rotation, magnetic fields, and birth environments, creating a spectrum of outcomes. Some neutron stars may have exotic interiors, where densities exceed atomic nuclei, potentially forming quark matter, where protons and neutrons break down into their constituent quarks, though confirming this requires observations that push the limits of current technology. Studying neutron star masses and radii helps constrain the equation of state for dense matter, revealing how matter behaves under extreme pressure, conditions impossible to replicate on Earth, making neutron stars natural laboratories for fundamental physics. Gravitational wave detections from merging neutron stars provide additional data because the waves encode information about how the stars deform during merger, and this helps distinguish between different theoretical models of ultra-dense matter, advancing nuclear physics through astronomy. Black holes also come in varieties, from stellar mass black holes formed in supernovae to intermediate mass black holes possibly formed through mergers to supermassive black holes at galactic centers, each requiring different formation scenarios and playing different roles in cosmic evolution. Intermediate mass black holes, with hundreds or thousands of solar masses, remain somewhat mysterious, with only a few candidates identified, possibly forming through runaway collisions in dense star clusters or through direct collapse of massive gas clouds in the early universe. Supermassive black holes, as mentioned earlier, reside at the centers of most large galaxies, including the Milky Way, and their masses correlate with properties of their host galaxies, suggesting co-evolution through processes that link black hole growth to star formation and galaxy mergers. When galaxies merge, their central black holes eventually sink to the center, forming a binary black hole system, which then spirals inward, emitting gravitational waves until the black holes merge, creating a single more massive black hole and releasing tremendous energy in the final moments. These galactic mergers are common throughout cosmic history, and they drive galaxy evolution, triggering starbursts, feeding black holes, and reshaping structures, creating the diverse galaxy types we observe today, from spirals to ellipticals, each reflecting a history of interactions and mergers. Our Milky Way will eventually merge with the Andromeda Galaxy in about 4 billion years, and the collision will disrupt both galaxies. Though stars are so widely spaced that direct collisions between stars will be rare, and most will simply follow new orbits in the merged system. The merger will likely trigger star formation as gas clouds collide and compress, and the central black holes will eventually merge, creating gravitational waves that future civilizations, if any exist, might detect, assuming they develop the technology and survive the intervening eons. By the time this merger occurs, the Sun will already be evolving off the main sequence, approaching its red giant phase, so Earth's fate depends more on solar evolution than on the galactic collision, which will reshape the night sky but not directly threaten the solar system. Looking beyond individual stars and galaxies, we can consider the universe as a whole and how stellar evolution fits into cosmic history, from the Big Bang through the formation of the first stars to the present era of star formation and into the distant future. The universe began about 13.8 billion years ago in a hot, dense state, and as it expanded and cooled, matter formed, first as protons, neutrons, and electrons, then combining into hydrogen and helium during the first few minutes, creating the primordial chemical composition. For hundreds of millions of years, the universe was dark, filled with neutral hydrogen gas, drifting without stars, until gravity pulled the gas into dense clumps and the first stars ignited, beginning the era called Cosmic Dawn, when light returned to the universe. These first stars were likely very massive, and they lived briefly, exploding as supernovae, and their explosions enriched the gas with heavier elements, seeding future star formation with the building blocks that would eventually allow rocky planets and life. Galaxies formed as gas and dark matter collapsed into gravitationally bound structures, and stars within those galaxies continued forming, living, and dying, cycling matter through generations, gradually enriching the cosmos with metals, a process ongoing today, though slowing as gas supplies dwindle. The peak of star formation occurred about 10 billion years ago, when the universe was younger and gas was more abundant, and since then, star formation rates have declined as galaxies consumed their fuel and as expansion spread matter more thinly across space. Today, we live in a relatively quiet era, with star formation continuing at modest rates, and most stars in the galaxy are older, low-mass stars, while massive stars are rare and short-lived, contributing disproportionately to chemical enrichment despite their small numbers. In the distant future, perhaps trillions of years hence, the universe will exhaust its gas reserves and no new stars will form, leaving only remnants, white dwarfs, neutron stars, and black holes, drifting through an expanding universe, growing ever colder and darker. Eventually, even white dwarfs will cool, becoming black dwarfs, invisible spheres of carbon and oxygen, and the universe will enter a dark age with no light except faint glow from evaporating black holes through Hawking radiation, a process so slow that it spans unimaginable timescales. Black holes will dominate the far future as the only remaining massive objects slowly evaporating over Google years, a number so large it defies comprehension, with more zeros than atoms in the observable universe, stretching time beyond any meaningful scale. After black holes evaporate, the universe may contain only radiation, isolated particles, and expanding space in a state of maximum entropy where nothing changes and no structure remains, a cold, dark equilibrium where time loses meaning. This ultimate fate seems bleak, but it lies so far in the future that it's almost irrelevant, and the current era where stars shine, planets orbit, and life exists is precious, a temporary window of complexity in an otherwise simple universe. Some cosmological models suggest the universe might end differently, through a big crunch where expansion reverses, or a big rip where expansion accelerates, tearing matter apart. But current evidence favors continued expansion, with the universe growing larger, emptier, and colder, without end or reversal. Dark energy, the mysterious force accelerating expansion, dominates the universe's energy budget, and its nature remains unknown, one of the deepest mysteries in physics, requiring new theories to explain why space itself pushes apart, overcoming gravity's pull. Understanding dark energy and its effects will shape our knowledge of the universe's fate and of the ultimate destiny of stars, galaxies, and everything within, though the answers may require breakthroughs in fundamental physics beyond current frameworks and observations. For now, we observe and study, building models, testing predictions, and refining our understanding step by step through the patient work of astronomy, physics, and mathematics, unraveling mysteries written in light across billions of years. Within this grand cosmic context, individual stars may seem insignificant, but each one contributes to the whole, and each stellar life, from birth in a nebula to death as a remnant, plays a role in the universe's evolution, enriching space with elements and energy. The study of stars connects many fields, from nuclear physics governing fusion to quantum mechanics explaining degeneracy pressure, to general relativity describing black holes, to chemistry tracing element formation, integrating knowledge across disciplines into a coherent picture. Astronomers use light as their primary tool, analyzing spectra to determine composition, temperature, velocity, and distance, and photometry to measure brightness changes, tracking stellar evolution in real time, observing objects millions or billions of light years away as they were in the distant past. The light we see from distant stars left those stars long ago, so we observe the universe's history, looking back in time, seeing galaxies as they were billions of years ago, and this time delay gives us a view of cosmic evolution spread across epochs. Spectroscopy reveals stellar chemistry by splitting starlight into its component wavelengths and identifying absorption lines created when elements absorb specific colors, each element leaving a unique fingerprint, allowing us to determine what stars are made of, even across vast distances. Early astronomers discovered that stars have similar compositions, mostly hydrogen and helium, with traces of heavier elements, confirming that stars share a common origin and that nuclear fusion produces the observed patterns, validating theoretical models through observational evidence. The presence of metals in stellar spectra indicates how many generations of stars preceded them, because population 1 stars like the Sun contain more metals than ancient population 2 stars, reflecting billions of years of stellar recycling and enrichment. By studying stars of different ages and compositions, astronomers reconstruct the galaxy's history, tracing how chemical abundances changed over time and how star formation rates varied, building a timeline of cosmic evolution from observations alone. This detective work requires careful analysis, comparing observations to theoretical models, calculating stellar ages, and accounting for dust absorption, which reddens starlight and dims distant objects, making them appear fainter and cooler than they actually are. Interstellar dust, composed of tiny grains, scatters and absorbs light, especially blue wavelengths, so stars behind dust clouds appear redder and dimmer, and astronomers must correct for this extinction to obtain accurate distances and luminosities. Infrared observations penetrate dust more easily because longer wavelengths scatter less, and space telescopes like Spitzer and James Webb observe in infrared, revealing hidden regions of star formation and distant galaxies obscured in visible light, expanding our view beyond optical limits. Radio astronomy also pierces through dust, and it detects molecules in molecular clouds, maps gas distributions, and observes pulsars, offering complementary information to optical studies. And together, these multi-wavelength approaches paint a complete picture of stellar and galactic processes. Gravitational lensing provides another tool, where massive objects bend light from background sources, magnifying and distorting distant galaxies, allowing astronomers to study objects too faint or distant to see otherwise, using gravity as a natural telescope. Some lensing events create multiple images, or ring-shaped patterns called Einstein rings, and studying these patterns reveals the mass distribution of the lensing object, even detecting dark matter through its gravitational effects, invisible except through lensing. The combination of different techniques, from spectroscopy to photometry, from gravitational lensing to radio astronomy, creates a rich dataset that astronomers use to test theories, discover new phenomena, and refine our understanding of how stars work across the full range of masses and ages. Each new observation refines the picture, sometimes confirming predictions, sometimes surprising us, and over decades, these observations accumulate into a detailed understanding that connects stellar evolution to the broader cosmos, revealing patterns that span scales from atoms to galaxy clusters. Stellar evolution isn't just abstract theory, it's testable science, grounded in observation and verified through multiple independent lines of evidence, from element abundances to light curves to gravitational waves, all consistent with a framework built over centuries of careful work. The predictive power of stellar models demonstrates their validity because astronomers can calculate how stars evolve, predict their lifetimes, and forecast their fates, and observations confirm these predictions with remarkable precision, validating the underlying physics and mathematics. This success inspires confidence that we genuinely understand stars, not perfectly, but well enough to describe their lives from birth to death and to place human existence within that context as products of stellar alchemy and cosmic evolution. The story of stars is our story, because we are made of stardust shaped by processes that began billions of years ago in clouds of gas that collapsed, formed stars, lived, died, and scattered their enriched remains into space, where gravity gathered them again, eventually forming the Sun, Earth, and everything on it. This cycle continues across the galaxy, with new stars forming from old remnants, and each generation slightly richer in heavy elements, gradually building the complexity that allows planets, oceans, atmospheres, and life, a progression that links stellar death directly to biological possibility. Without supernovae, there would be no oxygen to breathe, no iron in blood, no calcium in bones, no carbon in organic molecules, and life as we know it would be impossible, making stellar explosions, not destructive events, but creative ones, essential for existence. Every breath you take contains oxygen, forged in a massive star billions of years ago, expelled in a supernova, drifted through space, joined a molecular cloud, condensed into the solar system, became part of Earth's atmosphere, and now cycles through your lungs, connecting you to ancient stars through every inhalation. The carbon in your cells once lived inside a red giant, fused from helium nuclei in a hot core, then blown into space in stellar winds, and eventually incorporated into organic compounds on Earth, building proteins, DNA, and the structures that make life possible. This material connection is profound, linking individual human existence to cosmic processes and showing that we are not separate from the universe but part of it, composed of its matter, following its laws and shaped by its history over timescales vastly longer than human lifespans or civilizations. Recognizing this connection can change perspective, fostering humility about our place in the cosmos, but also wonder at the fact that the universe produces stars, planets, and beings capable of understanding their own origins, a remarkable emergent property of matter and energy evolving over billions of years. We are the universe becoming self-aware, a phrase that sounds poetic but is literally true because the atoms forming our brains and generating thoughts were forged in stars, and those thoughts now contemplate stellar evolution, closing a loop where matter studies its own history. This self-awareness allows us to ask deep questions about origins, fates, and meaning. And while stars follow deterministic physical laws, the emergence of consciousness adds a layer that physics alone cannot fully explain, hinting at mysteries that remain unsolved. Philosophy and science intersect here as we ponder what it means to exist as conscious beings in a universe of stars, and whether consciousness is common or rare, and whether it serves any cosmic purpose or simply emerges as a side effect of complexity without deeper significance. These questions may not have definitive answers, but exploring them enriches the human experience, connecting science to meaning and reminding us that knowledge of stars, planets, and evolution illuminates not just the external universe, but also our inner worlds of thought, feeling, and purpose. For now, we continue observing, learning more about stars every year, discovering new exoplanets, detecting gravitational waves, analyzing ancient light, and building theories that integrate observations into coherent frameworks, advancing understanding through collaboration across nations and generations. The knowledge accumulated over centuries, from ancient astronomers tracking planetary motions to modern physicists calculating fusion rates, to engineers building space telescopes, represents humanity's collective effort to understand the cosmos, a shared endeavor that transcends individual lives and cultures. This shared pursuit of knowledge unites people across differences because the universe operates by the same laws everywhere, and discoveries made in one place apply universally, creating common ground based on evidence and reason rather than belief or tradition, a foundation for cooperation and mutual understanding. Astronomy in particular has a unifying quality because everyone can look up at the night sky and see the same stars, inspiring the same questions about what they are, how they work, and whether we are alone, fostering curiosity that bridges divides and connects humanity to something larger than itself. The night sky has inspired humans throughout history, guiding navigation, marking seasons, inspiring stories and myths, and sparking scientific inquiry. And while our understanding has deepened, the sense of wonder remains, a constant across cultures and epochs, reminding us that mystery persists even as knowledge grows. Today, light pollution obscures stars for many people, especially in cities, and this disconnection from the night sky diminishes a connection that humans have had for millennia, but efforts to preserve dark skies and promote astronomy help maintain that link between people and cosmos. Seeing stars with your own eyes, away from city lights, is a powerful experience that no screen or photograph can fully replicate, because the direct perception of light that traveled across vast distances creates a visceral connection to the universe beyond intellectual understanding. If you have the opportunity to visit a dark site and spend time under a clear night sky, I encourage you to do so, because that experience can shift perspective, reminding you of the scale of existence and the fact that you are part of a universe far grander than daily concerns, a humbling yet liberating realization. The Milky Way stretches across the sky, in dark locations, a river of stars so numerous that they blend into a glowing band, and knowing that each point of light is a sun, possibly with planets, perhaps hosting life, adds depth to the visual beauty, transforming simple observation into cosmic contemplation. As we approach the end of this long journey through stellar birth and death, it's worth reflecting on what we've covered and what it means, not just as scientific facts, but as a story that connects past, present, and future across scales that challenge comprehension but reward patience. We began in darkness, in cold molecular clouds, where gravity slowly gathered gas until collapse began, forming protostars that heated and spun, then ignited fusion, becoming stars, shining steadily for millions or billions of years, depending on their mass. We traced how stars burn hydrogen, converting it to helium through fusion, releasing energy that supports them against gravity, and how they evolve as fuel depletes, moving through stages determined by their starting mass, each path leading to a different end. Low-mass stars, like the Sun, eventually shed their outer layers, forming planetary nebulae, and leave behind white dwarfs that cool slowly over eons, fading into darkness but preserving their mass in a dense sphere supported by quantum pressure. Massive stars follow a more dramatic path, fusing heavier elements in their cores, building layers like an onion until iron accumulates and fusion stops, causing the core to collapse and the star to explode as a supernova, scattering enriched material across space. The remnants of these explosions become neutron stars or black holes, depending on core mass, and these objects represent the most extreme states of matter, compressed beyond normal limits into densities that challenge imagination and test the boundaries of physical theory. We explored how supernovae enrich the interstellar medium, with heavy elements enabling rocky planets and life, and how binary systems produce novae and other phenomena, and how gravitational waves from merging remnants reveal events invisible to light, opening new observational windows. We considered the broader cosmic context, from the first stars in the early universe to the present era of ongoing star formation, to the distant future when stars will cease forming and the universe will darken over timescales that dwarf human history by factors beyond counting. Throughout this journey, we've seen that stellar evolution is not isolated but connected to everything, from the formation of planets to the possibility of life, to the universe's chemical and structural evolution, making stars central players in the cosmic drama, shaping galaxies and enabling complexity. We've also seen that science provides tools for understanding these processes through observation, theory, and experiment, building a framework that explains not just what we see, but why it happens, rooted in fundamental laws of physics and chemistry that operate everywhere across all time. This understanding is humanity's achievement, built over centuries by countless individuals who observed, questioned, calculated, and shared their findings, creating a body of knowledge that belongs to everyone, freely available to anyone curious enough to explore it, a gift from past generations. And it continues growing as new discoveries emerge, from better telescopes, more sensitive detectors, and deeper theoretical insights, ensuring that our picture of stars and the universe will keep evolving, becoming richer and more detailed with each passing decade. The story of stars is not finished, because stars continue forming, living, and dying, and because humans continue learning, observing, and wondering about the universe around us, driven by curiosity that seems fundamental to human nature, an impulse that connects us to the cosmos. In learning about stars, we learn about ourselves, our origins, our place in space and time, and our connection to processes vastly larger than individual lives. And this knowledge, while sometimes humbling, also inspires awe at the beauty and complexity of existence. The atoms forming your body traveled through stars, experienced fusion, survived explosions, drifted through space, gathered into the solar system, became part of Earth, and now constitute you, carrying a history, billions of years long, written in nuclear reactions and gravitational collapse, a legacy you embody simply by existing. That history continues forward through you, and through all life on Earth, as matter cycles through ecosystems, and eventually, billions of years hence, when the sun dies, Earth's atoms will scatter back into space, perhaps joining new clouds, forming new stars, continuing the cycle that has no true beginning or end. In that sense, stellar death is not an ending, but a transformation, where matter changes form and energy redistributes, and the process continues, cycling through states, from gas to star to remnant to gas again, driven by gravity, powered by fusion, shaped by time across the vast expanse of the universe. This cyclical view offers a kind of cosmic perspective, where endings and beginnings blur, and nothing is truly lost, only transformed. And while individual stars die, the universe continues, creating new structures from old material in an ongoing process that has persisted for nearly 14 billion years and may continue far longer. Understanding this cycle doesn't diminish its wonder, but deepens it, because the more we learn, the more intricate the connections appear, linking tiny quantum processes to galactic evolution and showing that the universe operates through layers of cause and effect that span scales from subatomic particles to superclusters of galaxies. We live in a universe that creates stars, and stars create the elements that make planets and life possible, and life, at least here on Earth, has produced consciousness capable of studying stars and understanding this grand cycle, closing a loop where the universe examines itself through beings made of its own substance. As this narration draws to a close, I hope you found it calming, informative, or helpful for sleep, whatever your intention when you started listening, and I hope the slow pace and the steady rhythm created space for quiet thought or gentle rest without demanding attention, allowing you to drift. The universe is patient and vast, and it operates on timescales that make human concerns feel small but not insignificant, because within that vastness we exist and we matter to ourselves and to each other, and that meaning is something we create through awareness, connection, and care. Stars will continue shining long after we're gone, and new stars will form from our atoms in the far future, and the cycle will continue, indifferent to individual lives, but beautiful nonetheless, a grand process that deserves appreciation simply for existing, for creating complexity from simplicity and light from darkness. So take a slow breath, let your mind settle, and know that you are part of this story, connected to stars through atoms and history, and that this connection is real, not metaphor, a physical lineage stretching back billions of years and forward into an open future where the universe continues, creating, transforming, endlessly unfolding.